There is something inherently delightful about watching a 2D plotter going about its business. Maybe it's just a simple fascination about drawing with the kind of accuracy that one would never be able to replicate oneself. I don't know what it is. I just know I find it very meditative. I wanted to make a plotter that draws on glass. Specifically, I wanted to make a vertical plotter that draws with chalk on windows. Why? Well, because I wanted to utilize the glass as frames for works of art. If you look out of your window often enough, you tend to get quickly familiar and even bored with the view. So why not fill the frames with nice designs? There's so much wonderful stuff out there. But of course, it doesn't have to be just for the windows of your own home. You could decorate shop windows or other types of vertical surfaces. But for now, I want to share how I accomplished this on glass surfaces with an Arduino Uno coupled with a cheap CNC shield. The design is of two aluminium extrusions. The top gantry is fixed to the window by suction force. I paid about $8 for this suction cup variant, which has a design that lends itself well to holding the aluminium extrusion in place. The stepper motor mounts are 3D printed with a T-nut-shaped protrusion that helps them slide onto the gantry. A single T-nut screw secures the mount. That screw is deliberately offset from the stepper motor so as to allow the motors to be extended beyond the length of the extrusion. I designed it like this because different windows have different widths, and to accommodate this, we can then easily extend the extrusions by adding straight connectors to any or either side, and adjust the motor placement by loosening the single screw and sliding the mount to where we want it. The gantry is also where we place the electronics, namely the Arduino Uno and accompanying CNC shield. The wire that holds the bottom X-axis is fishing wire wrapped around a 3D printed cylinder capstan with slanted sides that slides onto the motor shaft. Fishing wire, which, depending on the type, has the benefit of being thin and strong, and it slides quite easily, so the X-axis won't stutter in its movements, so to speak. The wire is wrapped around a block and tackle, so the braking force is actually multiplied. That's the design choice. A fixed y-axis could also work, but since different windows can have different heights, I wanted a design that was suitably extendable. This arrangement reduces the torque demand of the y-axis stepper motors. They would not be able to comfortably hold the x-axis by themselves. You'll notice this wire block also has a protrusion, which is meant for the end stops to interact with. The axis stepper motor is mounted on a 3D printed base plate that accommodates four wheels that fits on a 4020 aluminum extrusion, and onto the stepper motor shaft is mounted a pulley wheel that interacts with the timing belt that occupies the top slot. The belt is mounted on either side with a clip designed by Robin Wood that I came across on Printables and linked to in the description. The base plate also has extruded holes for mounting end stops, though I never saw it fit to actually get those to work. That's for another day. Two distinct types of spacers with different alignments of standard 608cc bearings can be positioned to fixate the axis to the window frame, and this then allows the axis to be moved in a controlled fashion. The configuration of the bearings may vary according to the window frame, but they are set on 8mm screws and can just be rearranged to accommodate the circumstances. The pen device consists of a housing and a servo-motor bracket joined by two threaded rods, one of which is longer than the other and features a wire holder that ensures the stepper motor ribbon cable and servo connector cable are kept out of the way. A pen is placed into the housing, into which a suitable spring is first added. When the servo motor is activated, the pen moves accordingly. I tried a number of variations, including mounting the pen directly onto the servo, but this design proved the best. The threaded rods provide some flexibility in adjusting the proximity of the pen to the window. Two threaded inserts offer the means to secure them in place, so the continuous activation of the servo doesn't push the pen backwards. The designs for the 3D printed parts are available via a link in the description to a public TinkerCad design. They all print fine without any need for support structures. Besides the 3D printed parts, all other components are standard and will be shown in details in the assembly section. They are available wherever. I got most of them from a decommissioned Creality Ender 3D printer that I got for next to nothing and took apart. From that came the stepper motors, some aluminium extrusion, wheels, timing belt and pulley, power supply, and so on and so forth. One big old suction cup is needed. This one cost me $8. The other main parts are of course the electronics. An Arduino Uno and a compatible CNC shield is all that is required to control the device. If you have not heard of the CNC shield, I hope to encourage you to check it out. A standard high-tech HS422 servo motor is used here to activate the pen. You can just use whatever you have lying around. The torque demand is quite low. Time to demonstrate assembling and mounting the device. Slide the suction cup bracket onto the Y-axis aluminium extrusion and secure it in place. Further fasten the extrusion to the suction cup with two T-nuts and screws that go into drilled holes that you will need to drill yourself. Secure the Y-axis stepper motors onto their brackets. Slide them onto the axis and secure them with T-nuts. No need to tighten them too tight now, you'll likely adjust the placement later on. Attach the cylinder cap stands to each stepper motor shaft. Slide each block and tackle piece to the back of the gantry adjacent to each stepper motor mount. The larger hole in the piece should be nearest to the motor. Mount the CNC shield onto the Arduino and mount those on the brackets and slide them onto the gantry. This is not a very elegant mounting design. I aspire to do better. The wire is first attached to the stepper motor capstan. It has a hole through it that we can thread the wire through. I'm using this knot that I learned. I believe it's called an adjustable Hitch knot, but I could be wrong. I'll be sure to link to it in the description. Cut off the remaining part when done. Secure the X-axis stepper motor to the base plate. As you can see, I got a bit ahead of myself and installed the pulley wheel to the shaft as well. Add the wheels. In my case, I got all of this from the aforementioned derelict 3D printer I took apart. I assume you can source these components if you don't have one to take apart yourself. Slide the motor assembly onto the axis. Add the two wire blocks to each end of it. Add spacers as per the configuration of the window frame. There's no need to tighten them just yet. That can wait until the fishing wire has been attached. I tightened them just enough so I can force them by hand until it's time to really fasten them down. The timing belt sits in the top slot and goes obviously below the V-slot wheels and above the pulley wheel. A pair of tweezers could come in handy here. The belt clips secure the timing belt to the aluminium extrusion. The clip is secured by a T-nut that goes inside the top rail. There is allowance for the belt to go under the T-nut that secures the clip, so there's no need to cut the belt to any specific length. In fact, it's desirable to have a non-fixed length, so you can work on windows on different widths without having to switch belts. Now for the fishing wire. To determine the length of it, measure the height of the window and multiply by 4 and add 1/2 for good measure. For now, I'll demonstrate with this shorter length, because that makes for the best demonstration. Thread the fishing wire through the bigger hole in the block and tackle. Then thread it through one of the outer holes of the wire block and back up through to the other side. Lead it all the way up to the block and tackle again and thread it from the bottom up through the block and then down again through the opposing hole. And back down to the wire block for one more round. And finally up again to the block and tackle. But this time just thread it around and fix the end with the same kind of knot or whichever knot you prefer actually, to secure it in place. Add the 2 threaded rods to the housing and secure them with 5mm hex nuts, preferably those with nylon insert locks. Add further hex nuts and slide the servo bracket over the rods and secure the bracket with additional hex nuts. Add the cord holder that ensures the cords stay out of the way of the window when drawing. Add the servo motor and secure it with 2 cable zip ties. The bracket has indentations for that purpose. I often incorporate these into my 3D designs because they're cheap and strong and save me a lot of filament and printing time. Now add the pen. I'll entrust you to modify the 3D printed pen housing to suit whichever kind of pen you prefer. The one shown here is marked S753. Maybe that's some sort of indicator as to its size. Add the spring to the tip and press it into the housing. Here I make use of 2 attachments that came with my high-tech HS422 servo motor. By electing to not completely tighten the screw that holds them in place, I can use the attachments as a sort of flexible zip tie, for lack of a better explanation. I push the arm attachment back to give space for the pen, and pull it back when the pen is inserted. If you don't have similar attachments, well, you'll figure something out, I'm sure. Finally, slide the pen holder to a suitable distance from the glass and secure it to the X-axis base plate by tightening the 2 screws into the threaded inserts. Wire up the 3 stepper motors to the CNC shield. Connect the servo motor cable. Here's a diagram of where to connect it to the CNC shield. The CNC shield needs a 12 to 24 volts input, preferably a 5 to 6 amp power supply. And of course you'll also need a suitable length USB cable. To control the device, we need to flash the open source GRBL software onto the Arduino. It is really hard to understate the significance of the work that the developers have put into making a, relatively speaking, weak ATmega 328 run this code that can turn any Arduino Uno into a fully fledged CNC machine. Although it has aged somewhat and newer alternatives exist, it's still right capable, and certainly for this project, the GRBL software has all that is needed. Well, almost. The GRBL project doesn't have support for a servo motor, but an industrious coder by the name of Claudio Prezzi has seen to this and added a GitHub repository with code that enables servo support. I'll link to it in the description of this video. Thus, what you need to do is to download the repository and open the GRBL upload.eno file in the Arduino IDE and upload that onto the Uno. To connect and operate, I use the Universal G-Code Center application that I'll link to in the description. For a dedicated introduction to the software, I suggest searching for applicable YouTube videos. For starters, all that is needed is to go to the Machine menu and click the Setup Wizard menu item and go through the individual steps. Of particular importance is the step calibration step. This allows you to calibrate and fine-tune the stepper motor steps versus the distance traveled when you activate the X and Y axis. Since the X axis works unhindered, but the Y axis is using a pulley system, there's bound to be a significant difference in the steps per millimeter traveled, and you will need to adjust for this. In fact, every time you set up the device for a new window, you should perform the steps, because this may incur a change in the distance between the device and the glass, which then has an effect on the calibration. After you have completed the wizard, you're good to control the machine. The jog controller should respond to your demands on the X and Y axis. And you can test the servo motor connection in the console window by issuing an M3 command followed by an S command with a value from 0 to about 15 or 20. You'll just have to experiment with the values here. There is one important aspect that I had better mention. If you type $2 in the console window and press return, of course, you'll be presented with a list of the configuration values pertinent to the device. Notice the one at the top, the $1 step idle delay. This indicates how long the stepper motors should hold their position after a G-code move has been completed. I'm deliberately setting this to 255 by typing $1 equals 255 and pressing return. And the reason I do this is so the y-axis stepper motors that are continuously loaded with the weight of the x-axis will maintain their position throughout the drawing. If one doesn't do this, there's a risk the y-axis will drift. This should not have a detrimental effect on the y-axis stepper motors because the pulley system greatly helps reduce strength on them, but the motors will become warm over time since they are never disengaged. It's okay if they become hot to the touch, but you should always be able to hold a finger to the motor frame without burning yourself. And it's always a good idea to turn the motors off when not actually drawing anything. So that's it for the device itself, a functioning machine for vertical 2D plotting. You can execute a G-code and issue commands to extend or retract a pen, and from here it should be a matter of effectuating designs of your own or someone else's making. I'll be the first to admit I'm not very diligent in regards to the creative arts, so I'll be on the lookout for copyright-free art. I particularly care for SVG files, since these can be imported into the GRBL plotter application that I'll link to in the description. This is another example of awesome open source software that you should definitely donate to, as have I, if you find use for it. Same with the Universal G-Code Center. It's awesome in how you can generate G-code from imported SVG files, and of particular note is how one can set up individual commands that will be inserted into the G-code when the generation senses a transition from one drawing path to another. Here's, for example, how I set up the pen up and pen down commands, where one G-code command moves the pen and another pauses for half a second to allow the x-axis to settle before the actual movement, the actual drawing, that is. I could easily sit there all day and look at this drawing process, even despite the fact that I know what the end result will look like. It's funny how that works. The basic design works okay, which isn't to say there's not a place for improvement. First of all, I should make those limit switches actually work and not just sit there for decoration. Secondly, I should design a better locking mechanism for the spaces. It's real bothersome to have to tighten them from the front, facing the window. And I want to design a pen holder that enables quick switching and different pen sizes. But for now, I'm happy and hope to have inspired and instigated creative thoughts and ideas. And I thank you for your time in watching this.